Thanks, Baruch, for the introduction. And also, I'd like to thank Dr. Rothblatt and her colleagues who organized the conference for the opportunity to address you. So this presentation actually is going to be a continuation of Dr. Hodgkin's presentation. It's just that one segment where she mentioned that 200 plus electrodes on the artificial retinal implant is problematic with respect to making contacts with the electrodes themselves. So here's the answer to your question. The next slide, please. Let me acknowledge my colleagues. Mark Humayun is a retina surgeon at the University of Southern California, the Keck School of Medicine. He is, in fact, the surgeon who pioneered the surgery for Second Sight's retinal implant. I'm not going to be talking very much about that, though. Pablo Panisi and Ken Yoshida are my colleagues at Aalborg University in Denmark, and the other names that you see are colleagues at the University of Tennessee and Oak Ridge National Laboratory. The objective that I've set for myself for the next 15 minutes is to convince you that there is a connection between photosynthesis, the natural process of how green plants grow, and the retinal implants that Dr. Hodgkins mentioned as a means for restoring sight to people who are blind from macular degeneration and retinitis pigmentosa. In order to do that, I'm going to give you a refresher course in photosynthesis. It's going to go real fast, but I know this audience can handle it. So what I'd like to do is explain the physics and chemistry of how green plants convert light energy into chemical energy. Of course, natural photosynthesis is all about plant growth, lignocellulosic materials. But how do those lignocellulosic materials work? Well, there are nanoscale photovoltaic structures that if you magnify that spinach leaf that I showed by a factor of 1,000,000, you see an organelle called the chloroplast. That is the smallest organelle that can do complete photosynthesis. Namely, it can synthesize cellulosic materials from carbon dioxide. But if we magnify by another 1,000, now we're down a factor of 10 to the 9th or 1,000,000,000 from the spinach leaves that I showed you. This is really what I want to focus on. And the presentation is going to be largely on this photosystem 1 reaction center. Green plants convert light energy into chemical energy by capturing photons and triggering a charge separation across this 5 nanometer photosynthetic membrane. That charge separation generates a voltage across the photosynthetic membrane, and it's that voltage that is the source of Gibbs energy that drives the thermodynamically uphill reactions of photosynthesis. So conceptually, the process is quite simple. The molecular photovoltaic structure, photosystem 1, is a particularly robust nanoscale photovoltaic structure. So the first part of my presentation is going to be focused on the electrical properties, the photovoltaic properties of this 5 nanometer structure: photon capture, charge separation, voltage generation. Then the next part, the final part of my presentation, is going to be focused on how this, in principle, might be used to restore sight to people who are blind from age-related macular degeneration and retinitis pigmentosa. Okay, the way in which conventional retinal prosthetic electrodes systems work, is that you have an external electrode and do electrode stimulation. And you pulse the neuron, and it's that gradient that is generated by the electrodes in the cellular medium that triggers an action potential. It works, no doubt it works, and it's doable, but it's not a particularly efficient way to stimulate neural cells. Suppose I could develop a nanoscale photovoltaic structure, such as the one that is in the photosynthetic membrane, which in nature is an integral membrane protein, and I extract that structure, I preserve its photovoltaic properties, and put it in a neural cell, in particular, put it across the neural cell membrane where the voltage ought to be. In other words, schematically, it looks like this. So rather than that electrostatic dipole that is generated by the external electrodes, suppose I take that nanoscale molecular photovoltaic structure, which lives its life in a photosynthetic membrane anyway, but now I put it back into a membrane, a mammalian cell, and now I ask it to do everything that it does in photosynthesis, namely absorb a photon and generate a voltage, but this time not do it in a photosynthetic membrane, but do it in a neural membrane, and in particular do it next to a voltage-gated ion channel, where that channel might sense the voltage that is generated by the system, and hopefully, maybe, that could trigger an action potential by the absorption of photons by the system. Okay, that's the general idea, the general program that we have in mind. So as Dr. Hodgkins mentioned, that in the artificial retina business, these are flexible electrode arrays that are placed on the surviving retinal neurons. The reasons the patients are blind is because the area of photoreceptors, the rods and the cones, are gone. But most of the retinal neurons are still functionally intact, and the wiring from the retinal neurons, the ganglion cells, for example, to the visual cortex is still intact. So the basic clinical result of the work that has been done by the retinal implant business is that you can do a partial sight restoration to people who are blind by judiciously stimulating these survival retinal neurons. Now, it shouldn't matter to those cells where the voltage comes from, whether it's a metal electrode or it comes from a nanoscale photovoltaic structure. So we're taking our cues from the clinical data that a judiciously applied voltage can evoke the perception of sight in people who are blind from macular degeneration. Here's the structure. It's a summary of its properties, and I'm going to show you the data that we have. We can extract these reaction centers and preserve their full photovoltaic properties. Typically, the open circuit potential of these nanoscale structures is a volt or more. And I'd like to explain to you how do we do that. We measure that in two ways. One is a trick by precipitating metallic platinum onto these isolated reaction centers and demonstrating the photoevolution of hydrogen. This is a closed circuit measurement. The current that's flowing, there are 2 electrons are needed to reduce 2 protons to 1 molecule of hydrogen. We know the redox potentials that are associated with hydrogen evolution. You need to generate species that are more negative than minus 0.5 volts in order for the reaction to go. So here's one experimental result that shows that even after we have extracted the reaction centers, we have still preserved their photovoltaic structures. Another way to do it is to measure the open circuit electrostatic potentials of these reaction centers. And here we use the techniques of scanning surface probe microscopies. So if you start with freshly cleaved mica and then grow gold epitaxially on that surface, dip the gold into mercaptoethanol and incubate that surface with a solution of isolated photosystem 1 reaction centers, I'll show you data that these reaction centers self-assemble on that atomically flat surface, and they assemble with the orientation of the electron vector transport perpendicular to the surface of that system. How do we do it? Well, we do it with a combined technique of tapping mode atomic force microscopy and scanning surface potential microscopy. On the next slide, I'm going to show you 2 maps of these reaction centers layered on the atomically flat surfaces. One is going to be a topographic map, which is measured where the output will be in nanometers. The other is an electrostatic potential map, which maps the reaction centers in electrostatic voltage. And here is the data. So the left is a topographic map. Each one of those green structures is a PS1 reaction center. But on the right, it too is a PS1 reaction center. You see there's a 1-to-1 correspondence between these 2 maps. The only difference, though, on the left, the reaction centers are mapped in topography. On the right, they're mapped in electrostatic potential voltage. These images are captured by a line-by-line scan in nanometer topography and electrostatic potential, and we construct those images simultaneously by going back and forth between topographic mode and electrostatic mode. The bottom line is that you could see, while all of this is going on, you see we have a diode laser that can illuminate the reaction center. While all of this is going on, we keep the light on and then switch it off. And you'll notice that as far as topography is concerned, it makes no difference whether the light is on or off. The elevation of the mountain is the same whether the sun is shining or whether it's nighttime. However, not true for the reaction center. When that light switches from on to off, first look at the polarity. The polarity switches from negative to positive just by virtue of turning the light off. How big is that voltage switch? Well, we can calibrate that scanning surface probe microscope, and here are the answers that we get for the open circuit potential of these systems. We have 12 reaction centers that are imaged totally in darkness, 22 in light, 4 that were on between light on and light off. The open circuit electrostatic potential is over a volt for these systems. So the take-home message of the modern biochemical methods of extracting photosynthetic reaction centers from tissue leaves is that they can be taken out and you can preserve the full photovoltaic properties of the photosystem 1 reaction centers. So now I'm going to take that as a given, that we have a procedure with market spinach or growing cyanobacteria that can produce genetically engineered photosystem 1 reaction centers. We now have a ready supply of nature's nanoscale molecular photovoltaic structures, which are going to be used for a variety of applications, and I'm going to discuss one such application for the remainder of my talk. Okay, so now we're back to the photosynthetic membrane, and I think everybody sees now where I'm going with this result. So while this reaction center loves to live its life in a photosynthetic membrane, I would like to get it into a neural membrane. I'd like to get it into a retinal ganglion cell membrane. And, well, how do I do that? If I can, you can see the benefits of it, that in close proximity to a voltage-gated ion channel, I might be able to trigger an action potential. Now, the data that I'm going to show you is not that, but it shows that we can impart photosynthetic optical activity to mammalian cells. Okay, here's the experiment that I would like to describe. We have no animals were harmed in the experiments that I'm going to discuss here. That we have tissue cultures of retinoblastoma cells, and we're going to add proteoliposomes. That's the trick for getting the reaction centers into the cell membrane. While the PS1 is an integral membrane protein, it is solubilized, it's purified, but now there's a few detergent molecules around it, so you've got to do something to get that membrane, that protein, into the cell membrane. And the trick is preparing photosystem 1 proteoliposomes. Then we load these retinoblastoma cells with fluorine-3, which is a calcium imaging dye. And we're going to shine light on that system. And then we're going to see if anything happens in a system where we have high concentration of calcium ions on the outside and low on the inside. The objective is to see if we can alter the permeability of the membrane of the retinoblastoma cells to have the light-induced movement of calcium ions into the retinoblastoma cells. Here are the optical properties of the system that's under consideration. The green line is the experimental curve of the PS1 proteoliposomes. It's largely the absorption spectrum of chlorophyll A. The solid blue line is the excitation spectrum of fluorine-3. The dashed line is the fluorescence emission spectrum of fluorine-3. Notice we've chosen the emission spectrum to be at the minimum where chlorophyll A absorbs, so we minimize the self-screening of the system and optimize the detection of the system. And also we use a diode laser, which is very near the red absorption maximum of chlorophyll A. Okay, here's the experimental technique. We're going to make, we prepare liposomes. Here are our isolated PS1 reaction centers. We reconstitute these PS1 proteoliposomes and then incubate them with the retinoblastoma cell. This is what our structure looks like. This is yet another technique to show that even after we have extracted the PS1 reaction centers, purified them, and put them back into the PS1 proteoliposomes, we still have photoactivity in the system. So we know we're good to go, at least in far as the photochemical and photovoltaic properties of the reaction centers are concerned. So here we're going to incorporate these PS1 reaction centers into the retinoblastoma cells. And now we have an experiment. And what we're looking at is the retinoblastoma cells after they've been incubated with these PS1 proteoliposomes. And we're going to pulse it with light. And so it's speeded up somewhat, but what we're looking at now is the light-induced movement of the calcium ions from the outside to the inside. Remember I said we had a higher concentration on the outside. Now this is not optically triggering neural cells, but what it is altering the membrane permeability of those cells so that we can show that in principle you can impart optical activity to mammalian cells by incorporating these photosystem 1 reaction centers into the system. These are simply control experiments. The top is the data. The bottom is if we leave out the PS1 proteoliposomes. This was published, by the way, in IEEE Transactions in Nanobioscience. So if you'd like to read the details, I can send you a reprint of it. And this is yet another control experiment, which I don't want to go into right now. Let me also conclude with the photophysics and photomodeling of these systems. So Pablo Panisi is a graduate student at Aalborg University who did a model system of incorporating the photosystem 1 reaction centers into the membrane of the liposome system. This is a finite element model, and mapped the electrostatic potentials in distilled water and in photosystem 1. And once again, even in that high dielectric environment, you can see that the voltages that are generated, if the PS1 reaction centers are in close proximity to voltage-gated ion channels, they should be able to sense the voltages that are generated by that system. Okay, so let me wrap up my presentation by summarizing what I've said, that artificial sight is a field that has great potential. And there's no doubt that patients are going to benefit from electrode implant structures, implant electrodes. However, as has been noted, there are real physical limitations. It's actually not just the metal contacts of all of those electrodes, but it is also the power that is dissipated by those multiple electrodes. 16 is not so bad, 60 is okay. Once you start to get above 200 and start approaching 1,000, you're talking about serious power that is being distributed in the system. So we think the next wave of the future is to use a self-powered molecular photovoltaic structure that generates its own voltage, and you do not have to bring in electrical power from the outside. So with that, I'll stop and try to answer any questions.
Thank you for that fascinating talk. I may have missed one part. The chemical structure is actually imported from the plants, or?
Oh yes, so in our experiments, it was market spinach leaves. And it's the photosystem 1 reaction center is just extracted from the spinach leaf, and we use it as is.
Right. And what plant was that?
Spinach.
Sounds right. Question, please.
Jun Lee from Kansas State University. I was told by my colleague those photosynthesis, the PS1 or PS2 are very unstable unless you embed them in membrane. But looks like for you, you don't need to take care of that. So what's the trick?
Right, okay, that's a good question. I would only agree with half of your statement. Photosystem 2 is unstable. Photosystem 1 is a robust protein. But let me define robust. If you put it on the lab bench for several days or even a week, it retains its activity. We're not talking about years and years of implants. So while they're robust enough, certainly, to do the proof of principle experiments, to do the laboratory work, to demonstrate the concepts of the ideas, without additional work in stabilizing the structures, or in fact, using other nanoscale photovoltaic structures, it doesn't have to be photosystem 1. We only use it because we know and love these molecules and we understand how to work with them. But suppose you had a semiconducting devices. For example, there are structures that are very CAD selenide capped with little metal nanoparticles. That induces an asymmetry, which too can be a photovoltaic structure. So I think of these more as proof of principle experiments to demonstrate that at least the concept is technically sound. But of course, you're absolutely right, that if one wants to get into real-world clinical applications, it's got to go in. And even Mark tells me it's not too hard to do an injection. We heard this nice talk yesterday by Professor Vishnawata on biodegradable nanoscale nanoparticles, where he got his nanoparticles with the green fluorescent protein to go to the back of the retina. So that part of the ocular cavity is accessible. There's no doubt about it. If you don't have to go in too often, maybe twice a year or 3 times a year, if the particles could be made that long, and I think that would be doable, then it might be the next way to get a much higher resolution. By the way, the pigments, unlike the electrode implant, you continue to use the optics of the eye. You keep in mind that if you put in metal electrodes in the eye, you're not using your visual system. There's a silicon imaging device that's out front that is stimulating the electrode array. Whereas if you resensitize the retinal ganglion cells, you can, once again, use the natural optical system of the person's eye. Sonia, do you want to?
Yes. Once you get your PS1 inside the cell membrane, how are you going to prevent it from diffusing?
Okay. And the answer to that is that PS1 reaction center loves a hydrophobic environment. It's got loads of hydrophobic amino acids around the waistband. It's only hydrophilic on the polar ends. So once it gets into that membrane, it's going to stay there. I mean, in fact, that thermodynamically, oh, you mean diffusing laterally. I'm sorry. Yeah, diffusing laterally. Okay. Yes, I could put enough of them in so that the probability that they're there at any one time would be that, or maybe a biochemical trick, a cross-linking trick between the amino acid residues of the ion channel and the amino acid residues of the protein. So that would be sort of a next level of sophistication in improving the efficiency and the coupling between the PS1 reaction center and the ion channel.
Darren Hurnett, DH Consulting. My first question is, if you use spinach, does everything look green? Just
No,
kidding.
No.
Just kidding. Feeble attempt
Right.
at humor.
And for the same reason that we use retinal in our rhodopsin and everything doesn't look orange.
Seriously, can you talk about the size of the photosystem 1 compared to the natural system and how that relates to the resolution that you can expect to get?
Right. So for those of us who work in the field of artificial sight, the holy grail of a metal electrode system is 1,000 electrodes. Now, Dr. Hodgkins pointed out the difficulty of just working, but let's assume you could do that. That forget about the materials problems of these 50 micron diameter electrodes. Forget about the difficulties of making electrical contents. We take that all as a given. It could do it. Then what does it buy you in all of that? You're going to have a hard time reading the New York Times if you had that 1,000 electrode system. At the very best, these are we have simulating systems where you could look through the world through 1,000 pixels, and you could sort of move it around, move your head, and 40-point font would probably be about what you could read. So there are limitations even with the electrode systems. However, our photosystem 1 systems, in principle, we can begin to approach the pigment density of our rods and cones because the size of those systems are compatible with each other. So it would be the functional equivalent of an electrode system of 1 million or 10 million electrodes because of the very small size. And we don't have those power problems that are associated with it because these are self-powered nanoscale photovoltaic structures.
Well, this may be facetious, but I seem to remember from my childhood that eating spinach was meant to be good for the eyesight. Is there some rational?
The answer is yes, but for a different reason. Right there, it's the beta carotene, but the beta carotene is long since gone in these reaction centers, which is a precursor for vitamin A. Right, so that's the.
It's good too.
But you're right. The connection is definitely there.
Well, thank you for that really stimulating and exciting